Hello again. Catchy title tonight. That'll maybe help the scoring on YouTube. Oops proposal. And we'll get into what oops we're talking about here. It's not a mistake, it's just an acronym. So there is evidence for celestial bodies out beyond Neptune, beyond what they call the Transneptunian objects. These are things like the Kuiper belt, the scattered disk objects, and detached objects. And then further out is the Oort cloud. And that's the first O in oops is Oort cloud. The Oort cloud is supposedly the origin of comets. These can be comets that we've never seen before, and they come in and they get too close to the sun, they crash into the sun. No harm to the sun. It's big. It can take it. Or they whiz past the sun and they go zooming back out to the far edge of the solar system. Those are repeating long-term comets. Halley being one of these, like 76 years. There's others that repeat even longer, 100 plus years, in which case you get it once in a lifetime to see it. We know these things because they come in from the outside and then they go back out, so we can track their orbits. And we have images of some of these things that are out there in the Kuiper belt: Pluto, Haumea, Makemake, Eris, and Sedna. Those are out what they think of in the Kuiper belt, or in the what they call the detached objects. They're far enough out that they're beyond the Kuiper belt, but we still know about them. We still have images of them. But to date, there have been no observations, nothing recorded, no pictures, no other evidence of anything in the Oort cloud itself. So if something comes in, we see it, we track its orbit, and we go, oh, that ellipse should wind up that far out and therefore in the Oort cloud. But we've never observed anything actually in the Oort cloud. Are they too small? Is the sun too far away for them to offer enough reflection for us to pick it up with our instruments? Are they not sufficiently reflective? If that's the case, then what size are these objects? They can be any size. You could potentially have an Earth-sized object out in the Oort cloud that's so far away that we can't see it. How would we observe these things? And that's where this proposal comes in, is the Oort Observing Proposed Solution. Catchy acronym that. Oops. Anything, NASA-ish that costs a lot of money, has a controversial design, it takes a long time to make it happen. It's maybe some technologies that are not yet proven. These sorts of observing programs often have catchy names when they first get initiated, and then later on their name gets changed, I guess, for better public image. How many people knew that the Pluto and Outer Solar System Explorer, POSSE, was what became New Horizon? POSSE rolls trippingly off the tongue. How can you call it POSSE, but there's only one of them? Back when I was growing up, I was taught that there's this thing called the Oort cloud out at the edge of the solar system. I was taught there was just one of them. You go out past the Kuiper belt and you get the Oort cloud. Turns out there's actually two of them. The inner Oort cloud is actually called the Hills cloud, and the outer Oort cloud, they left the moniker on it, and it's just called the Oort cloud. So the Hills cloud, the inner cloud, you can see the distance there. It's about 250 to 30,000 astronomical units. And I've got the kilometers and the miles and the light years for everybody that wants different units. That is considered to be a flat disk of field, very similar to the asteroid and Kuiper belts. It's stuff that was in the early days of the solar system thrown out, but not thrown out hard enough to make it go to the outer edge or to make it leave the solar system. It's kind of like, get out into the, Pluto, a little further range, and that's where it ran out of energy, and now it's on long elliptical orbits. But if there's enough stuff out there, it can interact with one another, and the orbits could be altered slightly by things passing by things, and the orbit that was once elliptical could now be more circular. And if the object goes from an elliptical orbit to a circular orbit, it will never get to the inner part of the solar system. It'll just be out there, and we have not seen it and might never see it, but it's out there. It could be lots of them. Could be Earth-sized things out there. And then there's the outer Oort cloud, or just the Oort cloud, and it's 30,000 to 200,000 AU. The thing there is that goes out to 3.2 light years, and the nearest star to our solar system is about a little over 4 light years away. So we're well on the distance out to the next solar system. So things out in the outer Oort cloud, or the Oort cloud, can be jostled by the Oort cloud of the other star system, sort of rubbing up against our Oort cloud. And so you can have things that are elliptical becoming circular, and you can have things that were circular becoming elliptical. But the other thing that is out there is once you get past the influence of our sun, our star, you wind up in the essentially the interstellar plasma system, and that has a certain amount of radiation pressure to it. So if something was thrown out far enough to be in the outer part of the Oort cloud, then the interstellar wind could actually push on it and change its elliptical orbit to something more circular. So these things could be in large quantities, and there's indications that the Hills cloud could have tens of thousands of objects in it, and the Oort cloud, which is not a flat disk, it's spherical around the whole solar system. There could be millions of Oort cloud objects. Initially, they thought of these as, well, they're just, leftover pieces of ice and dust and things like that. So they're all small. And then comets started coming in from out there, and they found out, wait a minute, these things can be hundreds of kilometers across. So what's the upper limit on their size? And that's where you get a lot of this Planet 9 kind of jargon of, it could be most of its time out in the Oort cloud and only a small amount of its time, maybe a few years at a time, into the inner solar system, then it swings back out. We would only know it by how much it jostles other things. And that's where they do the computer simulations. They find out, we think there's a ninth planet. We've just never seen it and don't know where it is because space is big. So how could these things no longer be seen? Most of the time when we see something, it's because of reflection. It's got ice on the surface of it or water on the surface of it, or it's like Neptune and Uranus. It's got a gaseous atmosphere, or it's hard rock that has like a metallic surface, so it's reflective. Things that aren't like that are thermal. They have internal heat, like volcanoes on Venus, and we see them through the James Webb Space Telescope by the infrared light source. And objects that are not too far out, let's say out as far as the asteroid belt, we can usually observe those using radar, using radio waves we send from Earth that bounce off the object, come back, and if we scan the object, we can actually get a rough look at what the surface of the object is, enough so we can actually tell its spinning, its rotation rate. If you send radar out a distance that takes 20 hours to get there and 20 hours to get back, that's a good long time. If you were trying to do that with something that was out in the Oort cloud, the radar echo would take years to get back, years to get there, and then years to get back. So we don't do radar that far out. No reflectivity, no infrared, no radar. How would we see them? Well, the next thing is something called the angular size. This is basically in the telescope's field of view. How big is it? How many pixels is it? And if something is far enough away, even if it's the size of the Earth, if it's out in the Oort cloud, that's far enough away that you might only see in today's resolution 1 or 2 pixels worth if it was reflecting at all. If you're doing a synthetic aperture, like a synthetic aperture radio telescope, it might be 4 or 5 pixels, but it's still going to be very small. And if there's no internal heat source, no infrared, not reflecting, and the angular size is small, then if it's far enough out, you're not going to see it. Now, obviously, we've taken imagery of Pluto. We've sent New Horizons out to Pluto, and we've got images of the most attached object, which is Sedna. So we can see at least almost out to the inner Oort cloud, to the Hills cloud. We don't have technology that can see into the Hills cloud or further out in the Oort cloud, even if the object is the size of the Earth. Now, they'll say that it's implausible that something the size of the Earth is that far away, but they won't say it's impossible, because they originally thought comets that are that far out can't be that big. After all, it's just chunks of ice and dust. And then they found like 500-kilometer comets coming in. They didn't hit the Earth, but they swung around the sun and went back out to the Oort cloud. They weren't that reflective until they got in. And when they go back out there, we don't see them anymore. So something can be coming out of the Oort cloud or the Hills cloud into the inner solar system. We spot them, see the tail form, watch them go around the sun, tail, they go back out, out beyond Jupiter, and then we no longer see them again because their tail's gone. It sounds like the inner Hills cloud would be a great place for extraterrestrials to put an Earth observing station, because we couldn't see them, but they could see us. But it also sounds like if we could get something out to the Oort cloud, that would be a great place for us to observe the rest of the universe, as well as the Hills cloud and the Oort cloud. So how do we observe something that's not currently observable, well, we could make our instruments better. We could go for higher resolution or larger diameter, kind of like we did with the James Webb Space Telescope, or we could hook multiple telescopes together and do synthetic aperture. If we went from 1 pixel to 2 pixels, most of the time we probably still couldn't see them because they lack reflection and internal heat, and the angular size, instead of it being 1 pixel, is 2 pixel, is still not, it's within the margin of error for noise in the instrument. So, and a radar trip out that far would take more than a year, and the radar power would be greatly diminished by the time it went out there, reflected, and got back to the Earth, so we wouldn't see it. If we're going to see objects in the hills or Oort cloud, we need to send instruments farther out, farther than the Kuiper belt, probably farther than Sedna. We need an observing site that's going to be a stable, long-term platform, probably orbiting something out there. But since we've never seen anything out there, we don't know what we want it to orbit until we get it out there. Then we have to decide, do we want to do the inner stuff and just, get out to the inner rim of the hills cloud and then look out? Maybe we can only look out as far as the outside edge of the hills cloud and still can't see the Oort cloud. Because remember, there's 10,000+ astronomical units between the hills cloud and the inner part of the Oort cloud. Or if we put it on the far side of the hills cloud and we could look backwards as well as forward, then we could observe the hills cloud and the Oort cloud. That would be good. But we won't know where to park it until we get out there. The spacecraft is going to have autonomous navigation, AI at work kind of thing. Now, what instruments would we be using? Radar, because radar is going to give us the farthest reach, and it will deal with things that don't reflect other than radio and things that don't have an infrared signature. Because essentially, think of radar as we're bringing our own candle. So we shoot a radar beam and sweep that part of the sky, and anything that's out there that's big enough to reflect, we'll spot it. We can't do that from Earth because the signal is too far away. But if we had a radar instrument out as far as, let's say, the outer edge of the hills cloud, we could certainly see the hills cloud, and we could probably see maybe the inner up to the middle of the Oort cloud. Obviously, it's going to have a lot of AI, a lot of autonomous stuff, navigating, recording, detecting, analyzing, and then sending the results back to Earth. But the two key things are, this thing is going to be so far away, we need long-term propulsion. So anything that would launch from Earth with a fixed size fuel tank, it's out of the game. That's not a solution. And anything that can't produce long-term power, and by long-term, I mean decades. If you think about the Voyagers, they're at 50 years out, and they're running on a fraction of the power that they originally had when we launched them, because even plutonium decays over time, and they're now down at about, instead of it being 35 kilowatts, I think they're now down to less than 10 kilowatts. RTGs for a really long-term solution aren't going to cut it. So how do we do propulsion absent a fixed fuel tank? Of course, it's my old favorite, radiation reflection pressure. We want something that's going to last for decades. Ion propulsion's great as a concept, but it runs on a fixed tank of gas, fuel. When it runs out after about 10 years, it's not going very far, not going anywhere. That's why the one that was in a asteroid belt object decided, well, I guess we're just going to stay in orbit until we crash into it. Now, that far out from the sun, if we haven't developed the technology yet for fusion or antimatter, then you're not going to do Bussard collectors of interstellar hydrogen and use those as kind of a super ion propulsion. But for the radiation reflection pressure, since they're so far away from the sun, we can't rely on the sun for the photons. We have to generate our own photons. And it would not be a solar sail because the sun's too far away. It would have to be localized. Yes, the technology would have to be researched, products designed, tested, and then we select that as the solution. So not near term. But we also need a long-term source of electrical power. That's on the next slide. And once we have radiation reflection pressure, and we're not running on a fixed fuel tank, we have long-term power, now we have unlimited propulsion. Even if it's only tiny, minuscule fractions of a Newton per photon, we can scale it up to dozens of newtons, which would be more than sufficient. Ion propulsion of the spacecraft that we've already sent out to deep space, those are measured in thousands of a Newton. Millinewtons. So if we could scale it up to dozens of newtons, that propulsion would still be additive, just like an ion drive, but it would be so much faster. And very quickly after launch, it would be going faster than anything we've launch today because it would be additive. And if we have multiple of these drive units, we want to put on multiple of them to make it easier to change direction and for redundancy. Does not require warp drive, does not require nuclear fission or fusion drives. This is a different approach. The farthest we've sent things with solar panels, photovoltaic cells out is Juno at Jupiter. And it has solar panels that are the biggest solar panels. It's got one on each side of this Juno craft, and they fold out like a stack of cards. That's what we needed to get enough power for a few kilowatts to run Juno at Jupiter. If you're going to go out past Jupiter, solar panels, photovoltaic cells aren't going to do it. You're too far away from the sun. But you're too far in to pick up any of the plasma from the interstellar medium if we could actually do that. So in the past, we would use plutonium decay, generating heat that we pick up with thermocouples and convert to electricity. That's called radioisotope thermoelectric generation, or RTGs, and that's what Voyager 1 and Voyager 2 uses. After 50 years, they're now down to a small single kilowatt power. If you use RTGs, after about 20 years, you're not running on the same power level as you did when you launched. We need something that runs on the same power level for the entire mission duration. We need something that's omnipresent and inexhaustible. And there's this thing called the Casimir effect, or something akin to it. It will generate picowatts per collected point. So you'll have to scale it up to get kilowatts. You'd really like it to be approaching 1 megawatt because you've got a lot of things you need to power. And maybe 2 or 3 generators at that level for redundancy. But once you have that level of unlimited power generation, there's no more fuel tank to worry about, and it'll last longer than an RTG, so you've solved the problem once and for all. But once you have that, maybe you should think about using it on Earth or in satellites that orbit the Earth or in satellites out at L2, so they don't give out after 5 or 10 years. We need that much power for all the things we're going to be doing with this Oort Cloud Observing instrument. Navigation, computation, including some AI stuff, powering the propulsion, doing the radar-based observing, and long-distance communication with Earth. But maybe for redundancy and for a number of other reasons, you might want to have more of these going out there than one. If we do what we did with New Horizons and have it just kind of do a flyby thing, and then it just goes on forever, people will lose interest in it. Because if it's 5 years from the last observation to the next one, people lose interest, it loses funding, and they shut it down, like they wanted to do with New Horizons. That's if you wanted to move from one celestial object to the next. We don't know where we're going, and we're going to select an object once we're en route. So maybe you could park somewhere for an extended period of time, do some observing, and then when you covered that area, you move on to the next location. But if you have unlimited propulsion and unlimited power, you can do that on a regular basis and maybe generate enough momentum that you won't do what New Horizons does, which is kind of bend its orbit around the next thing to get to the next thing to get to the next thing, use gravity assist, which doesn't give you all that much propulsive force. But you want to keep it in orbit. You don't want to land on some thing out in the Kuiper belt or the Hills cloud, because if you're going to land there, you're going to have to go through re-entry heating through its atmosphere. And once you get down to the surface, you may find that it's like Venus, and the surface is inhospitable to your instruments, and it'll be end of mission. Staying in orbit makes sense. And also, if you're at a Hills cloud object on the inward side, you're not going to be able to observe out to the Oort cloud. But if you park into an orbit on something that's on the outer edge of the Hills cloud, then you can see inward and you can see outward. And, if you're going to build an instrument like this, maybe throw on some amount of optical or infrared capabilities. And now that you're the better part of a light year out, you get a better look at those stars and exoplanets that are not too far away from us. You obviously don't want an orbit that's synchronized to whatever body you're orbiting, like a geosynchronous kind of thing, because it'll rotate and it'll rotate away from the Earth. And then you'll have periods of time where you can't contact Earth. So maybe 3 satellites or 4 satellites would be the right approach. So you send 4 of them out there and they separate out into an orbit around the object you're orbiting. And now as it goes around, you can send signal back to Earth and you can relay from one to the other. That way you're always observing the inner, the outer, deep space, and you're always communicating with Earth. Now remember, Earth is going around the sun on a shorter duration orbit than the things out in the Oort cloud. You're going to need something like the NASA Deep Space Network to maintain communications with Earth. And because you're so far out, the best approach would be to use lasers and use high energy lasers And so you want to build something that's like the Deep Space Network, but instead of orbiting the Earth, you want it to be multiple satellites orbiting the sun. That way it can always be in contact and then relay contact with the Earth, even from the Earth's perspective when the sun is in the way of where the object is in the Oort cloud. So you can always communicate, which is a good thing. As the Earth orbits the sun and as the Oort cloud has the object moving in it, the distance from the Earth to the object that it's orbiting can change by millions of miles. At certain periods of time, that object and the sun will be in opposition to one another with the sun in the middle. So you really need this UDN ultra deep space network that's orbiting the sun using lasers. So if you're going to be out of range for a while and you've got this thing that's scanning where there could be many thousands of objects, it's going to be like the Rubin Space Telescope that every 24 hours it's going to discover hundreds to thousands of new objects that have never been seen before. It's going to have to hold on to that data until it can get it back to Earth. It takes a long time to send the data back, and things may be blocking it. From its perspective, something in the plane of the solar system, like, I don't know, Saturn, Jupiter, Uranus, Neptune, can get in the way of communicating with Earth. You have to store a lot of stuff. So maybe think about putting petabyte scale storage per satellite. And, if it goes behind the sun, then you're going to have to wait until it comes back out again before it can relay the data. So in summary, the hills in the Oort cloud system exist. They're far enough away that non-reflecting objects with no internal heat have not yet been observed. And there could be Earth-sized objects out there that we've just never seen. And you won't be able to see those things from Earth-based instruments, Earth-orbiting instruments, or even objects like James Webb Space Telescope at L2. There's minimal to no reflection, no IR source, and they will be so small at that distance that you just think of it as pixel noise rather than an object. We won't know where we want it to go, so we'll need to determine our observing site en route using AI. It'll have to be fully autonomous operation for navigation and finding a site and orbiting it, and it'll be too far away. It'll be, better part of a year for the radio signal to say, should I orbit this one? I'll come back next year when you give me an answer. No, it's going to have to decide on its own. And it will require technology we have yet to develop, long-term power and long-term propulsion. I think observing would probably be by radar because that has the most range and, broadest sweeps, but maybe throw in some optical just to keep the budget money flowing. Communication at high data rates with that probe going to require laser communication. So we need something that works better than the Deep Space Network because the Deep Space Network is getting congested as we put more things out there. And also by having this new ultra deep space network, we can avoid the issue of the sun getting in the way. The new technologies and getting these things built and getting them launched out to deep space, that's going to take more than 10 years just to develop it. If you're thinking it's going to happen short term under a current budget or a current administration, that's just not going to happen. It's going to be multi-decade, multiple administration, multiple budgets long. Oops, the Oort Observing Proposed Solution. Yep, you heard it here first. Maybe someday somebody will give it a better name. There was a project once called Deep Space One. This is what we took, I think it was 8 different new technologies that were fresh out of the pan, and we tested them as best we could on Earth. We put them all into one deep space probe called Deep Space One, and that's where you get autonomous navigation, way before AI became an official thing. You got ion propulsion, you got radioisotope thermoelectric generators, RTGs. You've got star tracking. We're using multiple cameras to live track a star to know that you're in the right place. All of that was Deep Space One. It all proved maybe not 100% successful, but certainly viable enough to put more effort into it. Oops can be the same sort of thing. Lots of new technologies, but once we get it out there and it's observing for us, it'll be a whole new world, as the saying goes. And then links. Okay, comments, questions?
Yeah. Yeah, you mentioned that it would be a good idea to have multiple repeaters or relays out there with the sensing machines nearby so you could really. It occurs to me, do we have any satellites that circle the sun so that if we're on the other side of the sun or wherever we might be in our orbit,
Yes.
we can still receive.
On Earth, we have three major, these are all NASA, we have three major observing stations. They're all radio astronomy. That's the Deep Space Network. They're spread across the globe in a plane 120 degrees apart from one another. So if we want to talk to Voyager, let's say just say Voyager 1. Voyager 1 is going to be in a certain place in the sky. And as the Earth rotates, one of the antennas will be in the direction of transmitting to Voyager 1. But the Earth's going to continue to rotate, and it'll be the second antenna that'll receive the echo of the radio signal back from Voyager 1. So we're already doing that kind of thing.
Yeah, but no, these things are still orbiting Earth. I'm thinking of making a satellite.
No. Voyager 1 is not orbiting Earth.
Oh, I know that.
The Deep Space Network is on Earth. It's not satellites.
That's what I meant. Oh, yeah.
Yes, there is another NASA communications satellite network called the Space Network. Not Deep Space Network, just Space Network. This is a series of geostationary orbiting satellites orbiting the Earth, and there's more than 4 of them. And all they do is they will relay signals from one place on Earth to another. So, for example, one of the Deep Space Network stations is in Australia, another one is in Madrid, Spain, and the third one is in Southern California. If the Australian Deep Space Network station is receiving from like Voyager 2, and it wants to relay that data to the JPL Center in Northern California, it actually takes the signal from Voyager 2 into Australia up to the satellite that's over the Pacific Ocean, and then back down to the Deep Space Network station in Southern California, and then up fiber optic links up the west coast of California to JPL. So we're already doing the relaying.
I wonder if there's any advantage to having satellites that circle the sun, though, not just the Earth.
Yes.
It might be more convenient.
We had 2 satellites that were circling the sun, and they were circling the sun at the L3 and L4, or L4 and L5.
Yeah,
I forget. Yeah, they were at the 2 Lagrange points that are between the Earth and the sun at opposite sides of the sun. And they're somewhat stationary there, but not permanently. So they would tend to drift and go whoop around the back of the sun and then go whoop around the Earth towards the other station. So they would circle around. And Solar Dynamics Observatory? No, stereo. They were called stereo because it was 2 of them. There was stereo A and stereo B. And one of them, when it went around behind the sun, we never heard from it again. Nothing happened. Bye-bye. Now, it's far enough away from the sun that it wouldn't have crashed into the sun. But if one of its rockets went a little wonky and it started to spin, we'd never be able to communicate with it anymore, especially if it couldn't get a signal with Earth. So we still have one of the stereo satellites, but not the other one. China, when they wanted to put a probe that landed on the far side of the moon, not the dark side, the far side. When they wanted to land a probe on the far side of the moon, how would they communicate with it? Because the moon would always be in the way. So they put a communications probe with other instruments, but they put a communications probe out at L2.
Oh.
That way, the Earth could contact that probe from China and then relay to the lander on the far side of the moon. And the lander on the far side of the moon could relay back out to that probe at L2 and back to China. So, yeah, we do relays quite often.
I guess we're getting good at relaying. Yeah.
Well, I mean, there are relays that most people don't think about until you point it out to them. The rovers on Mars, Curiosity and Perseverance, it's rare for them to send meaningful data back to Earth directly because they need high bandwidth. That takes a lot of power. So what they do is they send their observational data up to any one of 3 different satellites, 2 of which are NASA, 1 of which is European Space Agency. They send the signals up to those, and those, because they have solar panels and are orbiting, they're more likely to be in contact with the Earth more frequently than the probes that are sitting on the surface of Mars. The satellite relay is orbiting faster than Mars is rotating. Mars takes about 24 hours, so to speak, to go around. So if Perseverance and Curiosity are separated by about 70 degrees on the surface of Mars, then at any point in time, one of them can communicate with Earth, but the other can't. So they relay up to the satellites in orbit, and those relay back to the Earth. So yeah, we're already good at doing relays. I don't think it makes any sense to do what do they call them in navigation? Waypoint, way stop, something like that. Where it's along the path to your destination, but it's like a quarter of the way, a half of the way, three-quarters of the way. Those sorts of relays don't make much sense because you just shoot the laser farther. You don't have to worry about it. They're not going to make it any faster because they have to relay, because the relay actually takes milliseconds of time. It's better to have relays for things that get in the way than it is to have relays that are just relaying, like amplifying the information. So yeah, I would want to send three probes out into the near edge of the Oort cloud, the outer Oort cloud itself. And I want three of them at least. Four would be great, but three of them at least, so they can be 120 degrees separated as they orbit whatever object they're going to orbit. And that way they could always be in contact with the Earth. But since the Earth, from that perspective, goes behind the sun for several months, we're going to need a solar laser orbiting relay satellite that can relay to the Earth when the two are in opposition to one another. So not only is it all the new technologies, we have to build the new relays, put the relays in orbit around the sun before we ever think about launching this thing out into the Oort cloud. Long-term project.
Yeah, you mentioned that it might take 10 years or so.
Maybe 10 years just to develop the technology,
right,
and another 10 years to develop the satellites and the actual deep space probes, and then 10 years to get them out there. So this could be a 30-year project. And you go, well, NASA doesn't do 30-year projects. You might want to go and look at the history of the James Webb Space Telescope. It's been around for a while.
I remember talking to some guys who were working on a satellite for doing something about the weather. And it took them about 3.5 years. They were developing this thing. And I'm talking to the engineers, and they were sort of down. They were feeling sad about what they were doing. And I said, this is great. Look what you're doing, you know.
Yeah.
And
because
they were saying,
once it gets launched, their career's over.
No, they were worried that they said, when we started this 3 years ago, we had an older technology. Things have developed and changed, and we're stuck building something that's 3 years out of date.
If you're lucky, yeah.
Same thing. If this is going to take 10, 20 years of development, by that time, there'll be all new improvements and new technological development.
You know how we solve that with weather satellites?
No, use an umbrella. I don't know.
No. We continually upgrade the weather satellite technology as the technology changes on Earth, and we always have another one in the pipeline.
Yeah.
So that's how we do it for the weather satellites, because we assume the data is important to avoid, monitoring for hurricanes and floods and things like that, storms. So we put up weather satellites, and for the U.S. we put what they call GOES satellites, GOES, and we put one on the eastern side of the U.S., we put one on the western side of the U.S., and they're in geostationary orbit, and they're looking down 24/7. They've got visual light capability, infrared capability. I think they've even got Doppler radar capability nowadays. They can monitor rain and tornadoes and such. But as soon as we get one launched, we're busy building the next one, and we launch it so that there's always a replacement in the queue for each of East and West. So it'll be like GOES East and GOES West were originally like GOES 15 and GOES 17. And they get renamed to being GOES East or West, depending upon which one. So they're planning out to like GOES 22 is the one in the pipe. So we need to think about doing the same thing. It's going to take so long to develop the technology that it's going to be obsolete by the time it gets out there.
Yeah.
So we need to put the best foot forward that we can. Test it, yes, make sure it works, but it's got to be
that's great for local satellites, things that are going in orbit, things that you can get up fairly quickly, but something that's going out to the Oort cloud or to Pluto or whatever, that falls into what Joe was talking about. Where
so we need to put them out there, and as soon as we get them launched, start building the next generation and get it launched too. This is a continuing program. This is the human species analyzing the solar system that it's in as like a protective or defensive item for the species itself. Because if the comets are coming in from the Oort cloud and we don't know what's out there and we can't watch it as it's coming in, how do we prepare for it? We won't see it until it's about Jupiter, and by then you got a year, and that's not enough time.
Even if we did notice something coming in, what do you do?
Well, I don't know. If it's really headed for the Earth and we don't want to spend the budget money to do anything about it, it's called duck and cover.
Yeah.
Yeah.
Climb under a rock.
Yes, or tuck your head between you and kiss it. Yeah. So we want as much early warning as we can, and we right now have these two giant clouds, one called Hills, one's called Oort, that we have no idea what's out there. And the only time we even know they're there is when they head in and we see them about Jupiter.
I'm all for it. I think that it should be common knowledge to educate everybody about our solar system.
I think so too, but I'm biased. But if you want a good example of the legacy of technology, whenever we have these unidentified aerial phenomenon and we send up like F-14 Tomcats with infrared cameras on them, and people go, is that the best we can send up? It's low resolution, low dynamic range, ratty looking. You can't make out any details on the surface of it. Is that the best thing we can do? My cell phone gets better pictures than that.
Yeah.
Well, what they don't realize is the infrared technology of the F-14 Tomcat is over 20 years old. What was your cell phone like 20 years ago? That's what's in the Tomcats. So when you're complaining about, it's always these fuzzy images that the military has. Well, that's because it takes a while to build the aircraft and add the technology. So when you see things like they're retrofitting a particular group of aircraft, let's say B-52s or A-10 Warhogs or F-35s with all the latest stuff we got, it might take them 5 to 10 years to get that technology retrofitted into the aircraft. And by the time they get it in there, it's outdated again.
Are you up on the latest technology from submarines? When they put up that scope, people don't look through a little.
No, they don't put up a scope anymore.
Yeah, look through a lens and see.
They put up a fiber optic cable that has a buoyancy thing on the top of it, and it has a camera on it, and that's what they look into is a giant TV screen.
Yeah, it's beautiful.
Yeah. And it's in color, and it can amplify light, and it can see in total darkness in infrared. Yeah.
They distribute the image all over the place.
Yeah, they can send it back to CENTCOM. Yeah.
The old submarine movies. Here, you look through it now. No, I'll look through it now. Yeah.
Technology. Any more comments about tonight's presentation before I stop recording? Hearing nothing.